Welcome back. So this is part 2 of the adaptive control lecture, where we will look at some interesting generalizations, and basically what you need to pay attention to is the idea of how we are developing these adaptive controllers rather than the specific problem itself. So once we get the hang of the idea, basically look at a particular problem and then try to understand how one can actually develop these update laws, and then prove, of course, stability, right? Both are equally important. Guessing how the update works is one aspect, but then proving is what is even more important, as I indicated through that NASA project experiment, right? So we will consider a scalar ODE, this nonlinear. So we're no longer in linear systems, and therefore is kind of nice. So what I assume is basically there exists a K such that this is true, right? It's quite artificial, it may seem at first, but what this is saying is basically this system is such that U can be chosen to be some linear combination of bunch of nonlinear functions through this Ki's and Hi's, and that kind of stabilizes the system, right? Using Lyapunov function x square, that's a different thing, right? So this is not really such a strong, it is a strong assumption for a class of systems, but you may actually very well find such systems where you don't know exactly what f and g are, but you know something more, something like this, right? So perhaps through some knowledge, f may have a bunch of parameters or some nonlinearities that you don't have exact values of each of those parameters, and those parameters themselves may be nonlinearly coming in, things like that, rather than a times x and things like that. So the standard adaptive technique may not work, but then if you can show something like this is true, the logic is basically I can estimate for Ki, right? So that's, again, it's very important for us to understand. In direct adaptive control, we are not interested in actually trying to estimate the functions f and g of the system accurately. Instead, if we know somehow to control through some parametric representation like here, then I can estimate the parameters and then get away developing those update laws and then showing stability, right? So what I'm going to show is, anyway, if this assumption is true, then with U equals summation of this thing, that closed loop is asymptotically stable, and it's a trivial exercise by using the Lyapunov function x square. I would welcome you to basically solve that, x square, take v dot, and then you'll get x times x dot, and x dot is f plus gu, and then u is chosen to be this, and then using this assumption we can show that this is asymptotically stable, right? Unfortunately, we cannot say beyond asymptotic stability, because these are highly nonlinear, and exponential stability and things like that may not be guaranteed, right? So now the assumption is basically we don't know the values of Ki, right? So under what conditions can we not know Ki? Perhaps a lot of f and g are unknown. We know something about them, we know form of them, and then we somehow magically figured out that this u works, right? But unfortunately, we don't know the exact values of Ki, which Ki works. So we are going to use adaptive technique to control such a system. So therefore, the usual technique is basically u of t is going to be replaced by summation of k hat times hi, k hat I times hi, and the k hat itself is basically update law given by minus alpha I, alpha some positive number, x times g of x times hi of x, right? So and then basically we can conclude that the adaptive control strategy guarantees convergence of x of t going to 0. The proof follows basically from this Lyapunov function, right? So let us actually perhaps see the proof once more, just to see how this technique works. Like I said, the important thing for you to pay attention is actually how I'm deriving the adaptive control laws more than the exact result, right? So I have this x dot equals f plus g times u, and I'm going to have this u is basically summation, some I equals 1 to n or whatever, k hat I of t, h I of x of t, h is known, ki is unknown, so we are estimating that with ki, and I'm going to basically have bunch of update laws for each of these i's, okay, ki's. So therefore v of x comma ki, right, k1, k2, and so on and so forth, is basically essentially half x square plus summation of alpha I k hat I minus k I whole square, right? Simple enough Lyapunov function that we've been considering. So this is coming from the error between the actual ki that we know that it works. We don't know the value of ki, but there is some ki that works, and I'm trying to estimate that unknown value of ki through this k hat. So therefore v dot is going to be x dot plus summation of alpha ki hat dot times ki minus ki. Perhaps there's a 2 here, right? Or let me put a half there and then eliminate this 2. Okay, so now x dot is f plus g summation k hat I h I plus all this. But what do I know? X times f plus g times summation of ki hi is less than 0. So I'm going to isolate that, add and subtract, so to speak, and I'm going to get plus summation of k hat I minus k times x g times hi, okay, plus this alpha ki. I could actually do this. I slightly modify the Lyapunov function, so I'm going to reverse the role of alpha in terms of, it becomes reciprocal 1 over alpha I ki times k hat I times dot times k hat I minus ki. Okay, all said and done, basically this part can be made 0 by choosing I is equal to alpha minus alpha. So I can replace that with minus alpha x times g of x times hi of x, right? So that's what we will get this term to be 0, and we know this part is less than 0, right? So again, going through the same kind of argument, v is going to be bounded. So we started with some value, some initial condition, v dot is less than or equal to 0, strictly less than for all x non-zero, and therefore basically we can say that this is bounded, and much more, it's integrally bounded. All the parameters that we see are bounded, and therefore we can even show x dot is bounded, therefore x dot is bounded, k hat is bounded, all those things are bounded, and then basically using the mathematical result that I showed early on basically concludes that x is going to be 0, right? So after a while it may get boring, but then once you should see enough examples for you to understand how this works, right? So this is a nice generalization of the linear system, but of course this assumption seems very strange. So therefore we will consider one example to see how this works, right? So if I had a polynomial system where these parameters are unknown, so then I immediately know that u can be chosen such a way that k1x plus k2x square plus k3x cube will be the one that stabilizes this particular system, for example, right? So of course the assumption is basically we know somehow these this system is in polynomial form, and I'll remark in a second. So there exists this u such that this stabilizes the closed loop. There's no doubt about that. So therefore we will use our adaptive technique, and then basically your k hat dot is going to be simplifying to be minus alpha I times xi plus 1, right? Now why this is quite interesting is basically any system locally can be approximated as a polynomial if it has sufficiently smooth conditions. So we can actually therefore kind of try this u in any case, right? and then basically do this adaptive technique, and then locally you'll have stability, right, under certain conditions. So if you have this local stability, then perhaps we can move on to the next point and then try a new adaptive control law and things like that. And then the original assumption was basically if things were slowly progressing, then things will work out very well, right? So of course theoretically it's much more difficult to prove exactly how this works, but at least if you can imagine basically any function can be approximated to a polynomial, then this technique works, right? So anyway, I'm not going to show the proof. The proof is we have seen it's going to be identical. It's a special case of what we have seen earlier anyway. But instead, let's look at the performance in Matlab, right? X of t versus t. So this is basically going to start at some initial condition, and clearly it's going down, right? So I mean, that's guaranteed from theoretical perspective. And how are each of the parameters doing? Well, I should have mentioned what values of a I picked, but I believe, if I'm not mistaken, not all of them are necessarily, let's say a1 is 1, then we know that k, the parameter that k1 that we are looking for, should be less than -1, right? But here you can clearly see that k hat is actually not converging to less than -1, but it's converging above -1. So here is an example where basically, just because k hat is converging to some number does not mean that that is going to provide a stabilizing controller. But the overall scheme, the adaptive law, the way it is, it actually provides stability, right? Convergence rather. So that's how. And let's look at one more example where this is slightly more generalized, and basically instead of looking at a scalar system, we'll look at a scalar second order system. So in that sense, it's a two-dimensional system where x double dot plus alpha times x dot plus beta times x is equal to u, right? And I want to stabilize u. Let me state the assumptions under which this works. So I'm going to assume that beta is such that x times beta x is greater than 0. It's a very special class of system. And more importantly, alpha is lower bounded. So that means some constant is there, that's less than alpha x. Okay. And this looks like a mechanical system where beta is certainly coming from a potential energy kind of a thing, either it's through gravity or a spring or whatever, and they all typically satisfy this x times beta x greater than 0. Whereas this alpha could be coming from many different things, including dissipation. If it's dissipation, then we know that it's lower bounded by 0, but sometimes this could be negative. You could have a negative damping case also, right, if it is not a mechanical system. So all I know about this particular alpha x is actually lower bounded. Can I stabilize the system? Well, since it is, also we assume that beta of x is equal to 0 implies x of 0. Let me state the fact and then basically explain how this works, right? So one of the things that we can show is basically if I pick u equals ax, a is less than alpha x, and then basically by bringing in this side, we can actually show that the system is going to be stable, right? So that's the assumption that we are going with. And basically, since I don't know much about alpha other than that it is lower bounded, I don't even know what is the lower bound, then can I control through adaptive law, right? So u of t, therefore I'm going to pick this estimate of a hat, and a hat is going to be this update law. Okay, so how does this work? Well, the proof follows from this particular Lyapunov function. Let me show. This is interesting enough. So we have this x double dot plus alpha of x times x dot plus beta of x is equal to u, right? So what I am picking basically is well, let's do this. X comma a hat minus a, which we can call as e. Okay, let's call that as ea. So half x square plus, I don't know, some gamma square or something like that over 2 a hat minus a, and somehow we need to use u and a hat dot to show that this entire system is going to be bounded, x going to 0 and things like that. This x dot square, and then this is square, and then we have some integral in terms of beta. Okay. So typically this comes from the potential part and things like that. This is a path integral if it is a multidimensional and things like that. So if I actually compute v dot, then I'm going to get x dot x double dot plus this part is going to give me x times beta of x times x dot. Okay. Plus gamma square times a hat minus a times a hat dot. Okay. So x double dot is x, I can take x dot common, x double dot plus beta x times x. Sorry, it's supposed to be x. Yeah. So beta times x, I'm going to basically get minus alpha of x times x dot minus x beta x plus u plus anyway this x beta x is there. So this cancels with this plus this gamma square part, right? So but u is chosen to be, so x dot times minus alpha x dot, and u is chosen to be a hat x dot, right? So I can add and subtract a x dot plus this thing over here, right? So I'm going to get x dot times minus alpha plus a, okay, which we know is less than 0. Why? Because alpha is greater than a, so 0 is greater than minus alpha plus a. Okay. So plus something to do with a hat minus a, and times x square, x dot square plus this gamma square a hat dot times a hat minus a. So this can be made 0 because a hat minus a is common. So a hat dot is something that we can choose, and maybe gamma square has to be inverse to get the exact answer in the slides. But essentially we're going to get minus less than x dot square times minus alpha plus a. Right? So again, going through the same logic we have been going through multiple times. Basically this entire thing can be shown to be bounded, therefore each one of those variables can be shown to be bounded eventually using that fundamental result in mathematics that we showed. X dot is going to go to 0, and then using zero state observability in this particular case we can show that it is zero state observable, and the fact that beta of x is going to be 0. So let's go through this. So x dot is 0, and then we can eventually show x double dot is 0. So as t tends to infinity, both of them 0. So u is, if u is 0, beta of x is going to be 0, so which implies x equals 0. So this system is zero state observable. So therefore we have stability x of t is going to go to 0 anyway. Much more, x dot is 0, a is bounded, x is bounded, and things like that. So these are different examples in terms of how one can extend the idea of adaptive control to, say, slightly nonlinear systems, but we make these assumptions. We have to know something about the system. It cannot blindly just think that I can solve this particular problem. But there is this assumption, like in the previous case, basically you can approximate anything with polynomial. What do we do with that error? That error perhaps is not going to destroy the boundedness. You can still show the system is bounded. You can reach close to the origin, but perhaps roam around the origin. Or in certain cases like this, basically we can show some technique, right? So the idea of basically estimating the parameters and of the controller, and then to get convergence of the state is what is the main idea, right? So we will end this particular lecture through this model reference adaptive control. We could have done this earlier, but I'm showing for the most general case where I'm going to go back to the linear system where x is now as a vector rather than a scalar. So the model reference adaptive control problem is simply designing an adaptive control strategy such that x goes to x hat. So x hat is a reference model. We don't want to go to 0, rather we want to track something, right? That track may be under our control sometimes, may not be under our control, but depending on which case it is, this can become impossible or possible, right? Here I make an assumption that I have complete knowledge of the model reference system, and in fact I can choose it if I want to. That's the assumption I make. So here we assume A is unknown, so the matrix A is unknown. B, A hat, B hat and reference are known or can be chosen, and I'm going to choose my reference model reference in such a way that A hat is perfectly stable Hurwitz, so that x hat remains bounded for any kind of reference. Because A hat is Hurwitz, basically we can find a P matrix, positive definite matrix, such that A hat transpose P plus P A hat is less than 0, right? So all the assumptions are made. The assumptions are basically A is unknown, right? It's completely unknown, constant, but it's unknown. B is known. A hat and B hat are also known, okay, and A hat is chosen to be stable and things like that. So corresponding Lyapunov function comes from this matrix P, and the following adaptive control strategy actually guarantees convergence of x going to x hat, where u is something, right? Now, what are these Q1s and Q2s? I mean, again, the idea is basically this is a direct adaptive control. I'm going to somehow estimate this parameter Q1, and Q2 is actually not estimated. Q2 is assumed to be known here, and then Q1 hat. It's a the last equation is a matrix update law. Q1 is a matrix typically, and but if somebody's confused about it, we can always take a matrix and write it as a long vector by taking each, stacking up each of the columns, but that we don't need to do, right? So what about this Q1s and Q2s? Q1 and Q2 are such that basically they connect between A hat and A, and that's Q1, and then Q2 is connecting B hat and B. Now B is known, and then therefore sometimes B hat can be chosen to be equal to B, and then Q2 becomes identity. So that part is easy. The more difficult assumption is basically I don't know this A, right? And then I'm basically making this assumption that A hat is going to be equal to A plus B Q1, where B is known but Q1 is unknown, right? Under what conditions can we guarantee? Well, don't think so much about it. In reality, this system, if it is controllable, basically A hat belongs to the controllable space, so stabilizable, sorry. So if it is controllable, we can always stabilize A plus BK or something like that, so that A plus BK is arbitrarily equal to some stable matrix, right? It's a very standard assumption. If AB is controllable, the result says that I can take my A plus BK to any matrix that is stable. So under such assumptions, basically I can pick A hat to be anything. I don't need to know Q1. I'm estimating over Q1, but such a Q1 exists, right, if AB is controllable. So I should have actually mentioned the controllability assumption, but under that assumption, this assumption is not so bad, right? So rest of it is actually straightforward, and I would probably leave this as a long homework for you to basically show stability. And this requires a little bit of understanding of how to take derivatives of matrices and things like that. This trace, I'm sure you know that trace of a matrix is nothing but summation of trace of a square matrix is summation of its diagonals. But if you take trace of some matrix times transpose of it, then that essentially is actually norm on that matrix. It's a basically a nice positive definite kind of function. It will provide a positive definite function for that. So trace of x transpose is non-zero if x is non-zero, right? So all those nice things will be there, and it requires a lot of homework on your part to actually show that this Lyapunov function works for this particular thing. And then, but otherwise the logic is same, the technique is the same. We show that v dot is less than 0, and then that shows the boundedness of x, u, and all the parameters that we have here, and including q1, and then eventually shows that x minus x hat is going to go to 0, right? Obviously here the Lyapunov function is, though it's a stabilizing, well, it's actually a reference adaptive control. It's not quite, we don't care about if x goes to 0. So of course one may question that basically should we choose x to be a hat to be stable? We need not, right? If it's not stable, then it becomes a little bit more complex, and we can still do this. We can certainly do an adaptive tracking of unstable system there, but it's a little bit more difficult and perhaps dangerous if we apply such things. But here we make this assumption to keep things simple, right? So hopefully you appreciate the technique of adaptive control, and we're not going to really get back and do much more than that. So what we have seen is basically, we saw how to stabilize, and then we use this Lyapunov idea over and over again to show closed loop stability in the control setup. Say in dissipativity case, we have this very simple result that says two dissipative systems and feedback could be made stable if certain things are true about the supply rates. Whereas in the adaptive control case, where we assumed certain parameters are known. So they're two very different type of problems, and each scenario demands its own solution. So far, so anyway, I mean, there are some more general techniques, and we might touch upon some of these things at a later point. Especially in the closing arguments, we will address some of the high level techniques. I mean, techniques are at a very high level without going into details of all possible ways to control systems and things like that. So we have this dissipated, we have this stable adaptive techniques. At least you have that in this thing, and then of course you can reverse engineer your standard Lyapunov function theorem to get controls, right? So, but none of these things are going to be optimal, because we'll pick something that stabilizes or tracks some model reference and things like that. So the next set of lectures, we're going to basically see how to control systems optimally, and then we will digress a bit and start talking a little bit about optimization first, and then get into optimal control. Optimal control can be quite subtle in terms of its arguments and things like that. Equally difficult in terms of basically solving them numerically or otherwise. Without optimal control, we cannot send shuttles to basically Mars and things like that. It's optimal control guys that keep on computing in terms of what the various control actions should be at every point and things like that, right? There are different kinds of optimal control problems. One of the first things that we will discuss is performance measure. What do we mean by optimizing something, right? So we'll come back and talk about optimization first, and then optimal control after that. Thank you.